Hello everyone, my name is Mohammed Salah. Today, me and my team are presenting our DDoS attack classification project. First, we will talk about the problem formulation and the points we took in consideration to choose the DDoS attack classification as our project. We have the danger of DDoS attack because DDoS attacks are one of the most dangerous cyber attacks out there because it can cause disruption of services, financial loss, and data breach. Also, it is very challenging to distinguish the type of DDoS attack, as it can exhibit distinct characteristics and require specific mitigation strategies. We have a tremendous number of features because there is a sheer volume of incoming network traffic, which is a challenge to monitor, and the variety of attacks vector because DDoS attacks can take various forms and utilize different protocols. Also, hackers' methods to make attacks more hidden as IP spoofing, botnets, and encrypted traffic, as they can leverage encryption to hide malicious payloads. It is very difficult for humans to detect it by simple programs because we have human limitation, as the speed and scale of DDoS attacks surpass human ability to manually detect and respond effectively, and the signal to noise ratio, as it's hard to identify malicious patterns within the overwhelming volume of normal network traffic. Now we will talk about the solutions that we come up with to solve the previous problems. First, we implemented a multi-classification for the different DDoS attack type because it's better to detect the specific type of the attack rather than making a binary classifier that only detect if an attack is present or not. Using a dataset like the CIC DDoS 2019, which is the newest version of the famous CIC DDoS datasets, ensuring data cleansing and pre-processing as data cleaning and data balancing, feature selection, label encoding, and splitting the data to different partitions. Using different modeling techniques like bagging, boosting, and implementing the newest and the most powerful models out there. Evaluating our model with different evaluation matrix and fine-tuning our model with different techniques to ensure that we can get the best performance out of our modeling process.
We used a dataset called CIC-DDoS 2019, which is one of the most popular datasets for DDoS attacks. This dataset focuses on classifying different types of DDoS attacks. It consists of many files, and we decided to use 4 files containing 7 categories. It's large data containing over 11 million rows and 87 columns. However, as you can see in these plots, uh, it's important to note that the dataset displays an unbalanced distribution across categories, which need to be solved, which will affect our model's accuracy and F1 score. Also, we will make the model biased to a certain class. So we needed to solve this problem, and this is what happened in the data pre-processing phase. Our first step involves data cleaning. This includes removing nulls and duplicate data and handling missing data to ensure the integrity of our dataset. After that, we focused on data balancing, where we distributed 1 million records equally into 7 categories, achieving a balanced distribution with 14.3% for each class through oversampling and downsampling techniques. Finally, we save these pre-processed records in a data frame, then exporting it as a CSV file, which can be easily reload for further work. And for exploratory data analysis, Andrew will continue.
Now we'll talk about exploratory data analysis. The first and easy property to review is distribution of each attribute. You can start out and review the spread of each attribute by looking at normal distribution using attribute histogram matrix. This is a random sample for distributions of our 87 features. This lets you note interesting properties of attribute distribution, such as possible normal distributions of attribute like destination port and timestamp. As we see here, we show correlation between our different features, representing strength and direction of correlation between different features from right to left and from top to down. Now we show here skewness for our features demonstrating how much probability distribution of random variable deviates from the normal distribution. These are box plots for our features demonstrating locality, spread, and skewness groups of numerical data through their quartiles. We can also show variability outside the upper and lower quartiles, defining different outliers in our data. Now I will talk about feature engineering and feature selection. Firstly, we use extremely randomized trees classifier or orchestra tree classifier to select our best 20 features to be used in model training later. Secondly, we perform a data standardization to standardize range of our features of inputted set. Thirdly, we split our dataset into training set and test set. And finally, before moving into model training, we implemented label encoding to convert all our categorical columns into numeric ones appropriate for the model. At the moment, data is ready for machine learning model, and now Muhammad Hani will talk about model building, evaluation, and fine-tuning.
After preparing the data for model training and selection, we initially created a random forest as baseline model based on reviews of previous papers. We then applied different models that can be categorized into traditional algorithms and ensemble methods, including bagging and boosting techniques. As demonstrated, we have implemented state-of-the-art models for DDoS attack problem distinct from previous work. After evaluating the performance of the training models using various metrics such as F1 score and accuracy, we visualized performance through the confusion matrix and ROC curve. Our evaluation indicated that our choice of ensemble techniques achieved high performance, proving that our implementation of state-of-the-art techniques is superior choice compared to traditional models. We also created two comparative visualization of classifier by plotting the F1 score and accuracy. This helped us observe the performance of each model and determine the best models. As observed here, ensemble models achieve high performance. To enhance our work, we fine-tuned the models through applied cross-validation, aiming for more accurate predictive performance. This ensures that the models not only fit the training data well, but also generalize effectively to new and unseen data. The results, as we can see, demonstrate that the models achieve high performance while avoiding overfitting. Additionally, we used a majority voting technique for ensemble classification to further fine-tuning. As we can see, the majority voting technique achieves high performance. Finally, we presented the overall performance result. Now Salah will review the project summary in conclusion.
At the end, we found that our model was successful in the detection of different DDoS attack types with exceptional performance metrics, as the accuracy and F1 score were above 99%, and this is because the efficient preprocessing and modeling steps which make our model a deployment-ready solution due to the ease of implementation and the scale and speed of preprocessing and training. Thank you for your time.